We are on Unit 4. This is Notes 2. Didn't put the little 2 in there. This is Notes 2, and it's on vertical and horizontal particle motion. Okay, so this is a section where we are still using what we learned last unit for function analysis. This is another type of application of function analysis. Okay, so in this application we have a particle, and the particle is either moving horizontally, so it's either moving to the right or to the left. Okay, so the particle is moving along a horizontal axis. Sometimes it goes to the right, sometimes it goes to the left, sometimes whatever. So sometimes it just is still, and sometimes it keeps moving, whatever. So there are lots of questions we can ask ourselves with that kind of movement, okay, that kind of motion. Or the particle is moving vertically, so maybe up, maybe down, maybe it's still for a while, and then maybe it goes down further, whatever. So we can have different functions describing that type of motion, okay? All right, so later on, FYI, later on in the spring semester, we will look at motion along a curve, okay? So in that type of motion, we'll be on a curve. So things like that, whatever, okay? So that'll be more fun stuff in the springtime, something to look forward to. Something to look forward to. I will tell you that students in general like this motion stuff, even that stuff, okay? It's not hard. There are some new terms to learn, but these are not hard things to know. So in general, kids like this quite a bit. They find it pretty easy. All right, so that's good. All right, let's dive in here. So on this first page of notes, we're just going over some definition of terms, okay? Or some concepts. So in general, t is time. But in theory, t can represent some other values, so we're going to always pay attention to any kind of restrictions that they have placed on t. A lot of times they'll say t is greater than or equal to 0, okay, if it is representing time. Okay. Know this though, t can be negative even if it's time. T can be negative, and this is the example I give for why t could be negative even if it represents time. So if t equals 0 represents noon, then t equals negative 2 would represent 10 a.m., 2 hours before noon. Okay? All right. S is frequently used for position. Okay, so S is frequently used for position. Other variables, of course, can be used as well. Most often, if you don't see an S, you might see an X if we're in horizontal motion, and Y if we're in vertical motion. Okay, so I would never use Y if we're doing a horizontal motion problem, and I would never use X if we're doing a vertical motion problem. But I can use S for either one of those. Okay. V represents velocity. V is always the velocity function, okay? And to find the velocity function, you take the first derivative of that position function, whatever position function it is. So the first derivative of position is velocity. Acceleration is, well, A of t is acceleration. And to find acceleration, you take the first derivative of velocity, which means you're taking the second derivative of position. Okay? All right. So S, V, and A are all functions of time. That's what this of t means all over the place, right? They are functions of time. So as time changes, these functions change. All right. Next up is speed. Speed is always the absolute value of velocity. Okay, so a lot of people think speed is the same as velocity. It's not. It's just the absolute value of it. Velocity can be negative, and if velocity is negative, that has meaning, and we're going to look at that in step 4 down here. But speed is always positive or zero. So speed can never be negative. Okay? Number 4, the particle is at rest when the velocity is 0. Particle is at rest when v is 0. The particle moves to the right or up when the velocity is positive. So if we're on a horizontal axis and velocity is positive, that means we're moving to the right. Okay? And if we come to a pause, then the velocity would be 0. And then if the velocity is negative, we're going to be turning around and going back to the left. So the particle moves to the left or down when the velocity, oh my goodness, there's a little typo, negative, goodness. That should be negative. I'm going to change that on yours so you'll never know that was like that. Anyway, then the velocity is negative. Velocity negative. Okay? All right, I need to make myself a note to change that on yours. Okay, it's changed. So you'll probably never see that. Hopefully you'll never see that. Okay, number 5, the displacement of the particle on the time interval from A to B, from time A to time B, is the value of your ending position minus the starting position. Ending position minus the starting position. Because it's always this, displacement can be negative. So if you end to the left of where you began, then displacement is going to be negative. So in other words, if this ending position was like -4 and your starting position was, let's say, 1, -4 minus 1 would be -5, right? So the displacement there would be -5. Okay. Quick note, after we have done integrals, so when we're doing motion along a curve, displacement, we can use, well, not only motion along a curve, but displacement is going to be this integral, the integral of velocity will be displacement. Okay? That's very useful if you have a calculator on your problem to know that. Okay, we'll do that later. To find the total distance traveled, you're going to add the sum of the total distances to the right and the total distances left. Distance is always positive. So let's say you're here on a horizontal line and you move some, let's say you're starting at 0. You move some to the right. You go over to x equals 5 on the right, and then you come back and you end over here at -10. What was your total distance traveled? Well, you went from 0 to 5, so that was 5 units, and then you went from 5 to -10, and that was 15 units. So your total distance traveled there would be 20. That's how you find the total distance traveled. Unless you know integrals and you have a calculator, and in that case, you just stick that little guy in your calculator. We'll be doing that later. Okay? All right. The last thing on this list is to know when speed is increasing or decreasing. Okay? This would be, increasing would be when your particle is speeding up, and decreasing would be when your particle is slowing down. Okay? To know when any function is increasing or decreasing, we take its derivative and do a sign chart, don't we? Increasing, decreasing, any function. Take the derivative, do a sign chart, right? So we would need to know the derivative of speed and do a sign chart on it to see when is derivative of speed positive and when is derivative of speed negative. The bad thing is that finding the derivative of an absolute value of a complicated function can be really horrible, okay, without a calculator. If you have a calculator, that's fine, but without a calculator, this is not pleasant to do. So here are the results. Here's what you're going to do if you have a question like this. The particle is speeding up, which means speed is increasing, when velocity and acceleration have the same signs. The particle is slowing down, which means the speed is decreasing, when velocity and acceleration have different signs. Here's the way to kind of explain that to you. If your velocity is positive, let's do a horizontal axis because I have lots of room here. If velocity is positive, that means you're going to the right. If acceleration is also positive, that means not only are you going to the right, but you're going to the right faster and faster and faster if acceleration is positive. So that means you're speeding up. If velocity is positive, that means you're going to the right, but acceleration is negative, then yes, you're going to the right, but acceleration is negative, so you're slowing down. You're still going to the right, but you're slowing down. Different signs, same signs. I could show you similarly if your velocity was negative and acceleration was negative or positive. Same thing, but here are the results, so know those results. Let's take a look at some examples. Example 1 is a no calculator example, and in this one it says the position of the particle that is moving in a horizontal line is given by this equation. So that's position, where t is measured in seconds with t greater than or equal to 0 and s is in meters. Okay. Part A, we're going to find the velocity of the particle at time t. So velocity at time t. Well, to find velocity, we take the derivative of the position function. So I need s prime of t. So we're going to take a derivative, 3t squared minus 12t plus 9. And that's the derivative of position. They did not ask me for any units, so I'm not going to give them any units. Unless they ask me for them, I'm not going to give them to them. Okay? Now, I get this question, Miss Murray, do I have to write that? My answer is yes. Yes, you have to write that. You have to write that s prime of t. Some of you are not going to like that. If you don't write that, then I don't know where you got this from. In calculus, in AP calculus, we communicate. Just doing problems is one thing. Being able to communicate what you're doing to do the problem is another. Okay? So here's my answer when kids say, do I have to write that? And here's what I would say. If you didn't write that, and somebody walked in who knows a little calculus, but not a lot, would they know where you got that from? Would they be able to tell you where you got that from? Okay? They may think, well, it looks a little bit similar to this, but not really. They wouldn't know. Okay? Communicate what you do. Because if you say this, then they're going to say, oh, they just took the derivative of s. Okay, that works. So communicate, always. All right? Next up, what is the velocity at exactly 2 seconds? What is the velocity at exactly 4 seconds? So we need the velocity now at 2 and then we need the velocity at 4. So we're just going to put 2 in for t. So 3 times 2 squared minus 12 times 2 plus 9. If this is a free response question like this is, it's not multiple choice, it's free response, I'm not even going to waste my time adding those together. Okay? Just leave it. The only reason that I would do it if this was multiple choice. So just leave that. V of 4 is 3 times 4 squared minus 12 times 4 plus 9. And again, I'm just going to stop. Do I need units? No, because they didn't ask me for units. If you'd like to put units, make sure they're correct. Because if you put the wrong units, I can't give you credit for your answer. Okay? That's how AP works. So if you do put units, make sure they're correct. Now if I asked you to indicate units, like in this next problem I ask you to indicate units, then usually the units will be 1 point and the answer will be another point. Okay? So that's a good thing. But if you put units when they're not asked for, better make sure they're correct because you might lose your answer point. Part C. Find the acceleration at time t and at time 4 seconds and indicate units of measure. I don't want to forget this, so I'm going to bubble it, and hopefully that will remind me to go back and get the units before I leave this problem. All right, acceleration at time t. I need to say what I'm doing. So I'm taking the derivative of velocity. And the derivative of velocity will be 6t minus 12. So the acceleration at time 4 will be 6 times 4 minus 12. They said to indicate units, so my units for acceleration will be, okay, the units for velocity would have been, since it's s prime, it would be units of s divided by units of t. So that would have been meters per second. You could write it out like that, or you could just write it in abbreviated form like that. Okay? You could even just do meters per second like that, and that's fine as well. So the way you write units in physics and stuff, that's perfectly fine to do here. Okay? So the units for acceleration will be, since we found it by taking the derivative of v, acceleration units will be units of v per units of t, right? Well, units of v are in meters per second. Units of t are in seconds, so we could write units per second, and that would be correct. Okay? We could also write this as meters per second squared, and that's correct. Or meters per second squared like that, and that's also correct. Okay? So I kind of go with this one, so that's what I would do there. Okay? Part D. When is the particle at rest? Particle is at rest. Okay, well the particle is at rest when, in fact I'm going to write that because I have to justify my answer anyway. The particle is at rest when velocity equals 0. That's when the particle is at rest. So I've already justified my answer. Okay? Now I just need to take velocity and set it equal to 0 and solve for t. So velocity is 3t squared minus 12t plus 9. I'm going to take that and set it equal to 0 to find when the particle is at rest. So here I'm going to take out a 3 because there's a 3 in everything, right? Okay. Now if I wanted to, I could divide by that 3. And if you divide both sides by that 3, it just goes away, and that's fine. Okay. I will tell you this though. Do not divide both sides by a negative. If this had been a different function and we were factoring out a negative number, don't divide both sides by that negative, because in this next part of the problem, we're going to need to do a sign chart on V in the next part. So if you divide out a negative, every one of these answers is going to be wrong. Okay? It'll be just the opposite, because you're changing the sign of what, if you divide out a negative, your V, what you get when you factor this, is not going to be equal to the V that you started with. Okay, I'm just going to leave my 3 outside, but I certainly could divide by that. So then we're going to factor what remains here. So T and T, 3 and 1, and then I need both of those to be negative. Take a second and FOIL this out and make sure you get that, you guys, okay? I hate grading a test and I can't give somebody credit for a problem because they didn't factor right. So take a second and FOIL that out. Make sure you get the same thing that you have over here. Okay. So T is equal to 3 and T is equal to 1. That's when the particle is at rest. They did not ask me for units. If they had, I would say seconds, right? They say to justify, but we did that at the beginning, so we are good. Part E. When is the particle moving to the right, moving to the left, and justify? So, particle moves to the right when V is positive. Particle moves to the left when V is negative. Okay, so all we have to do is do a sign chart on V. And in the step above, we found where V was 0. So those are my numbers that I'm going to put on my number line. And V it has to start, the time starts at 0, right? From my problem, time starts with 0. Okay? And then goes on indefinitely, supposedly. All right. So sign chart on V. So this is where I'm going to come up here and I'm going to put a number in here and use this here. This is where if we had divided by a negative, my signs would all be wrong. Okay. All right. So I'm going to put in like maybe 10. If I put 10 in for T, I have positive times positive. Everything's positive. That's positive. Since these zeros came from odd numbered factors, each of these has a factor of 1, right? Since they came from odd, this sign will alternate as we move. So negative and then positive, like that. So the particle moves to the right when in between 0 and 1 and anything over 3. You can write this in interval notation or inequality notation, either one. I think this time I'm going to use inequality notation. So in between 0 and 1, and when T is greater than 3. Okay? The particle moves to the left on T between 1 and 3. And that's it. So either inequality notation or interval notation, or you could actually write it out all in words if you really want to. Okay? We're pretty easy going. We need you to communicate, but you can communicate in a variety of ways. Okay? All right. Part F, we're going to draw a diagram to represent the motion of the problem. Okay, so let's begin by finding a few values of S, all right, of the position. I'm going to write again what my position function is so that we can see it. I'm just copying this down from above. Okay. Let's find where we're starting. Let's find the starting position. Where are we starting? Well, we're starting when time is 0 because of the problem. So when at time 0 we put 0 in for T and we just get 0. Now another good position to find is the position of the first time this particle changes directions. The particle changes direction the first time at time 1. So let's find that position. So the position at time 1 would be 1 minus 6 plus 9. Since I'm going to draw a little diagram, I do want to go ahead and find out what this is. So this, I believe, is 4. And then I'm going to find the position at the next time the direction changes. The direction changes at time 1 and 3, right? So at time 3, we're going to be at 27 minus 6 times 9 plus 27 again. And that turns out to be 0. Okay. And then after that, we're going back to the right indefinitely, right? Okay, so let's draw a little diagram, and there are different ways to draw a diagram of the motion. I'm going to do it like this. So I know I'm starting at position 0. So when time is 0, our position is 0. So I'm going to make this 0 and say this is when time is 0. Then we move to the right until we get to position 4. Move to the right until I get to position 4, and that will be time equals 1. Okay? Now I'm going to go to the left to position 0 again. Now if I just draw it right on this line, you're not going to be able to see it, are you? So because I want you to see it, I'm just going to come down below and say, okay, now I'm going back to 0 again. And I'm going this way this time. And that will be at time equals 3. And then after time 3, we're going to go to the right indefinitely. So there, and that's how I would draw a diagram. That's one possible diagram. You are not going to be asked to draw a diagram on my test. You're not going to be asked to draw a diagram on the AP exam, okay? But sometimes drawing a diagram will help you, okay? Especially when you're finding total distance traveled, okay? All right. Find the displacement of the particle during the first 5 seconds. Indicate units of measure. I don't want to forget that, so I'm going to bubble it. Okay. You need to know how to find displacement. Displacement is your ending position minus your starting position. What time are we ending? At time 5. What time are we beginning? At time 0. So I need S of 5 minus S of 0. S of 5 would be 5 cubed minus 6 times 5 squared plus 9 times 5. That's S of 5, right? Minus S of 0 is just 0. And since this is free response and this is a lone question, I'm not going to bother working it out. I'm just going to leave it. But I am going to indicate units of measure. What will the units be for displacement? How did you find it? Just with S. So this has units of S. And the units for S are in meters. Okay? Next up in part H, find the total distance traveled by the particle in the first 5 seconds. Total distance traveled. Okay. So here's, and I could, since I made the diagram, I could just go up and look at the diagram and be in pretty good shape here, all right? But since I want you guys to be able to do this anytime, even when I don't ask you for a diagram, and I already told you I'm never going to ask you for the diagram, right? So it might be good to know how to do this without a diagram. So first 5 seconds. So here's how to do that. Use absolute values, and on the notes page I talked about using absolute values for this. Use absolute values. You're starting at time 0, and with absolute values this takes care of itself. So time 0 minus, go to your first time, S at your first time that you changed directions. And the first time we changed directions was at time 1. That will give you your distance between those two spots. That will give you this 4 right here. Okay? Then add, now start at time 1 and go to the next time that your distance changed, that your, direction changed, and that was at time 3. Okay? That will give you this 4 units right here. And now you go, we want to go through 5 seconds. So S of 3 minus S of 5. And this process will always give you your total distance traveled if you're in a horizontal or vertical motion problem. Okay? So now we just have to go in and fill in the blanks. So S of 0 was 0, S of 1 was 4, whoops, S of values, plus S of 1 is 4, S of 3 is 0, plus S of 3 is 0, S of 5 was up here. So, I mean, if it's free response, minus 150 plus 45. You could just do that. And this is actually a safe stop spot. Okay? Absolute values are fine to safe stop with. This step above it would not be a safe stop spot though. Okay? So you do have to write it with numbers. Anything that you can put into a scientific calculator is a safe stop spot. Okay? If you can't stand that, you guys, that turned out to be 28 meters. Okay? Alright, part J, last part on this problem. When is the particle, when, so that would be time, right? When is the particle speeding up? When is the particle slowing down? Okay, well, here's where we look at acceleration and velocity, and do they have the same signs or different signs, right? So we already did a sign chart on velocity, so we have the signs of velocity. We need to do a sign chart on acceleration. So I'm going to take acceleration here. Here's my acceleration of t. I'm getting that from above. We already found acceleration. 6t minus 12. Set that equal to 0 because we want to sign chart it as well. So here t would be 2, right? So for our sign chart, we're starting at 0. I need 1 on my sign chart because it made v 0. I need 2 on my sign chart because it makes acceleration 0. And I need 3 on my sign chart because it made velocity 0, right? So I'm going to put acceleration on top. I'm going to put its signs on top, and I'm going to put velocity signs on the bottom. So velocity, remember, it was positive from 0 to 1. Velocity was negative from 1 to 3. Negative from 1 to 3. So negative, negative. And then after 3, velocity is positive. Acceleration only changes signs at time 2, right? So we can put like 1 in for time in for acceleration to see if acceleration is positive or negative on this stretch. So if I put 1 in there, I do get a negative. So this is negative and this is negative. The only time it changes signs is at time 2. And I know it is because this is a single factor. So it has to change signs here. So positive, positive. Now this makes it really easy to compare the signs. So different, same. Different, same. Okay, so for the sake of your notes here, we did these values on your sign chart. Write any time when V or A is 0. Okay. All right. For our answer, I'm going to come over here and try to squeeze this in. The particle is speeding up on 1 to 2 and greater than 3. So 1 to 2 and greater than 3. Since A and V have same signs. And the particle is slowing down on, okay, 0 to 1 and 2 to 3. Since A and V have different signs. Okay? So that was a no calculator problem, and it was quite lengthy. It did just about everything we can do. These other problems, these other examples are a little shorter. Okay? Example 2. The velocity of a particle moving along the y-axis is given by velocity is equal to t ln of t squared, where v is measured in meters per second. Find the acceleration at time 2. Okay. Well, acceleration is the velocity, is the derivative of velocity. Yeah. So we need to take the derivative of this. Okay, so it's a product. So I'm going to take the derivative of t times keep natural log of t squared alone the same, plus now I'm going to leave t alone and take the derivative of natural log of t squared. That is u prime 2t over u, t squared. Okay? We found the acceleration at time t, and now we need the acceleration at time 2. So acceleration at time 2 would be, and I just have to put 2 in for t here. So natural log of 4 plus, okay, my t's are going to cancel out here, 2. Natural log 4 plus 2. And that's it. Next up we have example. In this problem we get to use our calculator. So I'm going to grab my calculator over here. I probably have some stuff in it. I'm just clearing it out. Okay. So in this problem, the velocity of a particle moving along the y-axis is given by this function. A little bit complicated, right? Where v is measured in feet per minute. Find the acceleration of the particle at time 2 again. Indicate units of measure. I'm going to bubble that because I don't want to forget it. All right. We want to find the acceleration at time 2. Here's the thing. Our calculator can find a derivative at a given number for time. or for x, okay, at a given number. It cannot, my calculator can't just give me a derivative. Like my calculator would not give me this derivative here. Some calculators do. They would simplify that, but some calculators do, okay? Mine doesn't. The TI-84 does not. But we don't have to find it at time t. All we need to do is find the derivative at time 2. So if you have a calculator and you're asked a question like this, then we can find the derivative at time 2 without having first found the derivative at time t. All right. So here I'm going to go straight to a of 2. We're looking for the acceleration at time 2, right? So we're wanting a of 2. I still need to say what I'm doing. So it's the velocity, it's the derivative of velocity at time 2. Okay? Now it's time to use our calculator. So go to your home screen, and the first thing I need is we're taking the derivative of this at time 2. So you're going to go to the derivative. The easiest way I know of to get to the derivative function is to hit this math button, math, and then it's number 8 on your screen. So you can either scroll down, there it is right there, math 8. You can scroll down to there and put enter, or you can just push the number 8. If you push the number 8, you get that. Okay, either way. All right, and here's our derivative screen. Okay, in this first flashing box, you're going to put the variable that is in your problem. Okay, or you can just use any variable because the calculator will read it correctly. Now, whenever we put whatever variable we put here, it will automatically go over here. So we're taking the derivative with respect to t, x, y, whatever. This will automatically fill in for us. Okay. Now, I always use x's because it's so easy to get to on my calculator. So I'm just going to use an x there. And you can see it automatically filled in that x over here, which means every t, I'm just going to use an x. My calculator doesn't care, right? So my x's now will represent time. So now we're going to very carefully put this in. So I need sine of t cubed, so x cubed, divided by, in the denominator, I need parentheses around that denominator. If you don't, it'll only divide your x cubed by 1, and then it'll subtract x from the entire thing. So put parentheses around any sum or difference if it's in a numerator or denominator. Now I need to close my parentheses on the sign. Okay, and then cosine of, all right, natural log of t squared, so x squared, close your parentheses on natural log, and then close your parentheses on cosine. This other parentheses that is out there, barely able to see it here, there's another parenthesis out there, that's for the derivative in the calculator, so that will be automatic. Okay. And now we want to evaluate this when x is 2. Okay. So that gives me the derivative. We always round to 3 decimal places, at least 3 decimal places. You may go more than that if you want to, but don't go fewer. 1.079. Do not go fewer than 3 decimal places. If you want, I've had many students who just write the whole thing. Whatever's on their calculator, that's what goes on their paper. That's fine. I don't care. At least 3. Okay. Now I want units of measure. What units of measure would acceleration have? Well, it would have units of velocity divided by time, right? So feet per minute squared. Or you could write feet per minute per minute. Number 4. A particle moves along the x-axis now, so that its velocity for time greater than 0 is given by this function. Now this is a multi-step problem here, right? There's parts to it. So in part A, I'm doing the same thing I did in the previous problem. However, I know I'm going to be using the same function here over and over again. So I'm going to go to my calculator and I'm going to put that function in for y1. That way I can use it over and over again. And I don't have to keep retyping it in on my home screen. Okay? Natural log, tangent inverse is right here in blue, so second tangent inverse, e to the t. E to the t is right here, so second that button, and then t, I'm going to let x be t again. Close the parentheses on the inverse tangent, and then close the parentheses on natural log. Okay? Now, to find the acceleration at time 2, we are going to, we can do it two ways. I can do my home screen and do the same thing we did above. So math 8 with respect to x. And now, this is stored in for y1. The quickest place to get y1 from your calculator is to go over, see the F4? That's what you want to access. The F4 is in green, so you're going to do the green button here first. So alpha, and then F4. And this gives you your selection of all your y's. So enter. And then we want to evaluate this derivative at time 2. Like that. Okay. Now, what would happen if I just wrote 0.0925 or 0.093? If you do that, you will not get any credit whatsoever. You will never ever get credit for an answer that you don't show any work for at all. Don't communicate what you did to get it. Okay? So acceleration at time 2 is the velocity at time 2. I'm sorry, the derivative of velocity at time 2, and that is 0.09. I'm going to round that 2 to a 3, and that'll be good. Okay? They didn't ask me for units. I don't even think they gave me units, so no units on that. That's it. Okay? So that's one way to do this. Okay? Here's the other way to do it. If we go to our y equals screen, there's our function, and we can graph that function, right? I'm going to do zoom 4, and it'll graph that function. Now, this is the entire graph of the function, but I really only want it when time is positive, right? So I'm going to adjust my window a little bit and go, I think I might start maybe at -2, and then maybe I'll go to 10. How about that? And it looked like it didn't go very far on the y, so I think I'm going to go from like -1 to 1. Okay, so I really not concerned with these negative values. Okay? All right, so we want the acceleration at time 2, and acceleration is the slope of derivative at time, of the derivative of v at time 2, right? So the derivative of this at time 2, okay? So I can find the derivative of it at any point that I want. If I do calc, so the calc here, so second calc, look at what's here at number 6. That's the derivative. And I can move this to x equals 2. In fact, I think I can type in x equals 2. At x equals 2, it gives me the derivative right at x equals 2. And that's the same number that we found on our home screen, right? So that's another way to do it. Okay? All right. Part B. Is the speed of the particle increasing or decreasing at time 2? Is the speed increasing or decreasing at time 2? Give a reason for your answer. Okay, well up here we found that A of 2 is 0.093, and that's greater than 0, isn't it? What is V of 2? What is V of 2? Well, we have our calculator, we can do that. All I really need to do is trace. Here's my graph of V, trace, and then I'm just going to put in 2 for x, and now that's the value of velocity at time 2, right? That's the value of velocity at time 2. So it's 0.362, which is also greater than 0. The other way we could find out what the sign of V at x equals 2 at time 2 is to look, and it's right there, it's above the x-axis. If it's above the x-axis, then it's positive, right? The other way to do that, if you don't want to look at your graph, is to go to your home screen again. To find the value of V at 2, if I pull up y1 again, second F4, pull up y1 again. We want to evaluate that at time 2, right? Did you know your calculator can do this? If you do parentheses 2, it will evaluate your function at time 2. Many teachers don't even know that this does that. Same thing. Okay? So, we found that acceleration and velocity have the same signs. So the speed is increasing at t equals 2 since A of 2 and V of 2 have the same sign. Last little piece here. Find the time greater than 0 at which the particle is farthest to the left. Farthest to the left. And justify your answer. Farthest to the left. Okay, let's take a look at this. Here's our graph. We only want to analyze time greater than 0. In fact, for this, I think I will start at 0, so we only see where we want to see. This is the graph of velocity, right? So, on this little section, velocity is negative. On this section, velocity is positive. What's happening to this particle when the velocity is negative? When the velocity is negative, the particle is moving to the left. So on these times, the particle is moving to the left. And then for the rest of time, the particle moves to the right. So if we want to know when the particle is farthest to the left, keep in mind, let me say it again. Here, the particle is moving to the left. So if I had a different graph for just the movement, if I did a diagram for the movement, here velocity is negative, so the particle is moving to the left until it gets to this time, and then at that time the particle turns and goes to the right. So at this time, the particle is at its farthest point left, right? So that's a crucial time for us. I need to find that time. So to find that time, I'm going to put 0 in for y2 here. I'm going to put 0 in for y2, and then I can just do second calc. Intersection is number 5. Enter, enter, enter. That's the quickest way I know to find an x-intercept. Okay, let me do that again. I put 0 in for y2, graphed it, and then do second calc 5, enter, enter, enter. and it'll give that intersection point to you. Okay, so we need to justify our answer, not just an answer. Never ever just give a decimal answer or any kind of number answer without saying what you did to get it. Okay, I'm going to say the particle moves left on time 0 to 0.443. Then the particle moves right after t equals 0.443. So the particle is farthest left at t equals 0.443. Okay. So the particle moves to the left at this time. I didn't say why, so let me go in and say why, since v is less than 0 there. And to the right after that, since v is greater than 0 there. So the particle is farthest left at that time. Okay. Hopefully that makes sense to you. And it's logical too. Anything that's logical is a good justification. Okay? Alright. Alright. So time for you to go and try this. This was these were the notes for the entire section, but I think I have 2 different worksheets for you for this material. One is without a calculator and one is with a calculator. So you need to, don't think that just because it's with a calculator, they're easier. Because if it's with a calculator, all it means is that I can give you much more complicated equations for things. Okay? So be sure to practice both of those.